Welcome back to Arts Learning. In this video, we'll be going over something that's a bit similar to conservation of energy as well as Newton's third law and every force has an opposite and equal reaction force. We'll be examining both these concepts but in relation to momentum because momentum follows a very similar story which these do. Okay? So similar to Newton's law, right? Net force or just regular force, right? If a car hits another car, then we know that the force between them are going to be equal and opposite, right? So that's your force. We know that's going to be equal and opposite. And what else do we know? The time in which they're both colliding, right? Because one can be in collision with the other more time than the other one, right? So both of these collision times must be equal. Both of them must have the same time duration of the collision. Okay? So force times delta time. Both of these are equal, right? This car has the same force, same time. This car has the same force and same time. And what quantity is this? Impulse, right? Or change in momentum. So that means our change in momentum is the same for both of the cars. Right? It's the same because they're both the same car, same force, same time. So since impulse is force times delta time, change in momentum will be the same. Or in other words, momentum will be conserved, okay? Momentum lost by one object is going to be gained by the other. So take, for example, a cannon, okay? We've all, somewhat understood that when the cannon fires a ball, the cannon also moves back a bit, right? That's why people fire it from a further distance. But the ball moves front a lot. So what does that mean? Why does the cannon move back? So the cannon's total momentum is 0, right? Because it's not moving here. But then once it fires the ball gains a velocity, okay? It gains a very high velocity, but its mass is pretty low. But the cannon has a very high mass, but in order to preserve the momentum and not change it, it has to have a low velocity, right? And then the same momentum is preserved, which is 0. If you look at any system, the momentum after the collision and before the collision, the total momentum before is equal to the total momentum after. That's the principle of conservation of momentum, okay? So since this initial momentum was 0, the final momentum is also going to be 0. Both of these are going to tie in a way that the momentum is 0. Or another way you can think about it is both these objects, right, receive the same change in momentum. Because that's what this tells us, right? We know the same force, same time of collision. So this object has a low mass, so it's going to have a high velocity, right? But this object has a high mass, so in order to keep this same momentum, it's got to have a low velocity. That's why the cannon moves, but because it's very mass intensive, it moves only a little bit. The velocity is a little. Okay? So the momentum changes cancel, exactly. But since they're acting on different objects, they don't cancel each other out. It's just the total momentum of the system is conserved. And that is a principle of conservation of momentum. So, for example, right? So it's a very poorly drawn frog. That's the best I could do. If this frog, okay, was on a tree, and it jumped off that tree and came down on a skateboard, okay? The skateboard has a horizontal momentum this way. Will the skateboard slow, speed up, or stay the same? The skateboard will slow down, right? Because the only momentum, the horizontal momentum in the system, okay? Because there's vertical momentum here. But think about it as only horizontal for the skateboard because that's what we're looking at, right? For how fast it goes. So this this vector here, is the velocity, right? And that's for the skateboard. So we have a P initial. And we know that once this frog lands, P final has to be the same as P initial. So P initial is just the mass of the skateboard times the velocity of the skateboard, right? But P final is what? It's the mass of the frog plus the mass of the skateboard. So if you add an extra mass here, it makes sense that the velocity has to go down to conserve the momentum, right? Because this quantity, mass, went up, so velocity must go down to conserve this same initial momentum. So that's why the skateboard would slow down, okay? So that's how you analyze these kind of collisions using conservation of momentum. So let's just go through some conceptual questions before we actually tackle more math-based questions, okay? Which tie into collisions. Because conservation of momentum is very prominent in collision, right? Before a collision, we have a certain momentum, and after it, we have a certain momentum. So that's how it works out. A person on frictionless ice, right, throws a ball forward. What happens to the person? So initially, the ball is with the person, right? So P initial is 0. There's no momentum here. Nobody's moving here. But once he moves, so once he throws the ball gains some mass times velocity. It has low mass, but it has a high velocity, right? In order to conserve the momentum, this man must gain a negative change in that momentum. So negative velocity because it's going the opposite direction, and mass. But since his mass is higher, his velocity must be lower. That's why it's only noticeable when it's on like frictionless ice, right? But it does happen. Whenever you throw something, you're going to feel a recoil unless you're leaning into that thing. Okay? So two ice skaters push off of each other. Compare their momenta afterward. So that's the fancy word, right? Momenta. Let me draw the skating boots. Okay, yeah. So there's two ice skaters here, and they just push off of each other, okay? So what happens here? So the initial momentum is 0. Once they push off of each other, this one's going to go this way, right? It's going to have a mass times velocity. That's its momentum. And this person is going to go this way. Same thing, mass times velocity. Both of these momentums must be equal. So if they don't have the same mass, they must have differing velocities to match up for that mass. But they're going to be the same, okay? The velocity might be lower or velocity might be higher, but mass times that velocity should be the same. Why is the system's momentum only conserved when it's isolated? So think about it this way, right? For the cannonball system that I showed you earlier, initially the cannon had zero, the ball was in the cannon, right? So it has 0 momentum. Once it's fired, it has initial momentum, final momentum, in both directions. But imagine if I came in with a car and I bashed into this cannon. Then the momentum would not be equal, right? Because I'm adding my own momentum here. In order for there to be conservation of momentum, you must be looking at an isolated system. You can't add in external forces, otherwise you add in external momentum, okay?